Hello everyone, it's a pleasure to be here in the online edition of VLDB. Today I'm going to be talking about progressive indexes, indexing for interactive data analysis. I am Pedro Holanda, a PhD student here at CWI in Amsterdam, and this work was done by me, by Mark Rasveld, Stefan Monegold, and Hannes Muleisen. So let's start off by some very quick motivation. I think I have to convince no one here from the database community that creating indexes is a very complicated task, and this is mainly due because of the number of indexes one can create for a table. And to actually create them, you have to carefully analyze the cost of creating, maintaining, versus how much they're going to boost your workload. Someone from the audience can think like, yeah, sure, but this problem has already been solved. We have these self-tuning tools. They're capable of automatically creating indexes or at least giving good hints to the database administrator. And they do that by capturing relevant workloads and understanding through statistics which indexes to create to boost that workloads without being heavily penalized by updates. And they fully create on the magic midnight time of the data warehouse where no one's using the database. However, they don't actually work that well for interactive data analysis. And the reason is that in interactive data analysis, the workload is highly unpredictable. You have no prior knowledge, so you can't really capture relevant workloads. And you have no idle time to invest on a priori index creation because there's always a human in the loop issuing queries against the database and waiting for their answer so he can know what to query next. For the past 15 years, more or less, a set of techniques have been developed to create indexes in this exact scenario. They're called adaptive indexes, and they create indexes partially through query execution only on data that's being accessed. So to give you an idea of how adaptive indexing works, you can imagine that we have this column of integers and it's completely unordered. When the first query requesting elements between 10 and 14 arrives, adaptive indexing is triggered, and it works by making a full copy of this column and by running two quick sort iterations, each having the pivot equal to the query predicates. So this would cause the actual index to be cracked into three pieces, where the piece in the middle has all the elements between the two query pivots. So after performing these two quick sort iterations, you store the information of where these pieces start and end on a binary search tree. You can perform a lookup on this binary search tree. For example, here you know that you want the elements between 10 and 14, so you know that you need to scan the offsets between 8 and 12, and then you just scan those, and that's your query answer. And for the next query, when it's executed, the same process is going to be repeated. So you're going to again do quick sort iterations with pivots equal to the query predicates. And you can imagine that this process constantly refines whatever is being accessed more. So these pieces become smaller and more manageable. And how does this actually look like on a real interactive data analysis scenario? Well, here you can see the SkyServe workloads. To give a little bit of context, the full index takes about 47 seconds to be created. The average full scan is about 10 seconds, and the average of full index, it's almost 10 to the power of -4. And there are a couple of things that are pretty interesting to notice here. The first one is there's actually a pretty big penalty on the first query. Of course, 10 seconds is still 5 times faster than creating a full index, which is 50. However, this is also about 10 times more expensive than just performing one full scan. So you can imagine the scenario where the person is always scanning a new column. This never pays off. You're always constantly paying this 10 times X cost of a full scan. The second problem is that there's a lot of performance spikes. There's a lot of variation. On this workload, you're constantly zooming in on different pieces of your data. So every time you shift to a new piece, you can see you have a 4 orders of magnitude spike, for example. And the last problem is there's actually no guaranteed convergence. So even after executing 1,000 queries, you still has no guarantee that you're going to enjoy from this nice average full index cost. So we designed progressive indexing to solve exactly those three problems. And the basic idea is that all these problems are caused because we have no control of how much data we're indexing per query. So our idea is to make this incremental index creation and refinements even more fine-grained. So instead of performing, for example, 2 quick sort iterations on one query, we're actually going to have an indexing budget delta, and this delta is going to tell how much of the data is going to be index on that query. So in practice, we could run, for example, half one quick sort iteration, if that's what we want. And with this change, progressive indexing is actually capable of having a low impact on the initial queries, or at least as low as the user wants, a very robust query execution, and predictable and guaranteed convergence. So to give you an idea of how this looks like, again, the same column as before and the same query, but now with progressive quicksort with delta equals to 0.5. So that means the half our column is indexed on each query, or half a quicksort iteration is executed on each query. You can see here that the pivot selected was 10, and it starts by the first element 13, and decides, okay, 13 is bigger than 10, so it goes to the bottom of our column. 16 is bigger than 10, so it goes to the bottom of the column. 4 is lower than 10, so it goes to the top. And you do that to half the column. And the rest of the column, when you reach the half, you just scan. You don't copy and pivot to our index. And while you're performing all this scanning, you also can see here the elements in green. They are the ones that actually answer our query. So you do, in practice, one full scan, know which elements answer your query, and you copy half the elements to your column. And you store this information in a binary search tree. So you know that you're pivoting on 10 and where you started and ended on your index. The nice thing is when a second query now asking all the elements below 4 comes, you actually only need to scan the top parts of your index, because you know that's where all the elements below 10 are, and 4 is below 10. And you need to scan the other half of your column. And you continue performing the same pivoting. So for example, you go to 1 now, 1 is below 4 or below 10, so it goes to the upper part of the column, and so on and so forth. And by just scanning the upper part of our index and the bottom parts of our original column in this query, you have the query answer. And how does this look like again in the same workload compared to adaptive indexing? Well, now you can see that the first query is actually much cheaper than the actual adaptive indexing. This time about 3 times more expensive than the actual cost of a full scan, because here we have delta equal to 0.3. You can see that the query is much more robust. That's very low variance, and the variance only goes down, so you have no 4 orders of magnitude performance spikes. And you can see there's actually full convergence. So at some point, it's guaranteed that you're going to have done enough work to actually have built a full index and enjoy from the average full index cost. So in summary, all these 3 problems progressive indexing is actually capable to solve. There's a lot of future work to be done. So how do you deal with multidimensional queries? How can you build multidimensional indexes with progressive indexing? Of course, there's the problem of updates. You could do similarly to adaptive indexing on progressive indexing, but there's no guarantee of a robust or somewhat constant query execution. And that's the approximate progressive indexing idea. Of course, to keep these on interactive times, you need to guarantee that they are very fast. So at some point, if your column is too big, even a simple full scan can already be too expensive. So can we integrate progressive indexing with approximate query processing? Well, what else is in the paper? In the paper, we actually explore 4 different techniques of progressive indexing. Here, I only showed progressive quicksort. We actually have a cost model, so we don't have this turning knob of picking a delta, but you actually pick a time that you want your queries to execute, and the cost model automatically selects the delta. And there's a lot of adaptive indexing work out there. Here, I only showed you the first one called standard cracking, but in the paper, we actually discuss and compare against a bunch of those techniques. Well, thanks very much for your attention. Please, if you have any questions, shout now or email me or send me a tweet, and it will be a pleasure to discuss with you. Thank you.